Push that rock here with Simpson Math, talking sinusoidal waves. So by now we're familiar with the unit circle. And when we say the unit circle, we frequently just don't mean the circle whose radius is 1 and centered at the origin described by the equation x squared plus y squared equals 1. But we mean the actual diagram where the convenient angles are all labeled. By convenient angles, we mean the angles where we can find the coordinates either just using the radius, like here we know it's over 1 and up 0, and here down here we know it's over 0 and down 1 because the radius is 1. Or we can use the 30, 60, 90 rule, as we can do here at pi 6 and here at 2 pi thirds. Or we can use the 45, 45, 90 rule, as we can do at pi fourths and 3 pi fourths. So we call these the convenient angles. There are many, many more an infinite number of intersection points along the way. So sine has an infinite number of values. It doesn't just have 0, 1/2, 1 over square root of 2. Remember, sine is the y coordinate when you input the angle, but there's really tiny angles here. And then there's angles that just hit at random places on the curve that aren't so convenient. And one of the things you notice about the convenient angles is there's only a 15-degree difference here, or pi 12ths radians difference here, but it's a pi 6 radian difference from 0 to pi 6, of course, which is a 30-degree difference. So there's this big gap here. So if we were to graph just using the convenient angles, we have to be very careful about assuming the distance from here to here is not the same as the distance from here to here. Many beginning students just plot the graph as if this distance is the same as that distance, which is obviously not true. This arc length is clearly not as big as this arc length. So the fix is to get a common denominator. So the common denominator of 3, 4, and 6 and 2 is 12. And if we did that, we'd have pi 12ths, or which converts to 15 degrees. So there'd be a point here, and then we'd have these two angles. And then there would be a point here. But these points are, we can get these values. We can even get them exactly. And we will this semester using something called the double and half angle identities. But they're not as convenient. They're not so easily computed as pi 6, pi 4s, pi thirds. So pi 12ths is not as easily computed, and we don't necessarily need it to be able to see the graph. It's sort of like when you're graphing parabolas. You don't have to get every point on the parabola to see the U shape. Or graphing a line, you really only need 2 points on a line. So we don't have to have this point, but it's important to remember that if, on an axis, you have to label your increments in uniform increments. You can't just, I've seen these types of things on Fox News where, they have an axis like this. In fact, there was one just the other day. They had an axis like this that went, here was 0, and then it went 5, and then the very next one was 20. Well, you can't do that. That's just nonsense, okay? If you're doing that, and then the next one up, I forget, but it was really big, like 100. And so what they were trying to show was that COVID cases really weren't going that big. They were showing COVID cases. But if you make a jump like this, of course it doesn't look that big. I mean, this is just nonsense. That's the kind of thing you see on Fox News. So we don't want to do that. We want to be more professional. So keep that in mind. Now, I'm going to create a table of points. Anytime you're beginning at something, at a graph, you should create a table of points. This is not the table I wanted. Oh, this is the one I wanted to show. So what a lot of students frequently do is they go, oh, well, let's put on 0, let's put pi 6, let's put pi 4s, let's put pi thirds, because those are the convenient angles. But notice what we just did. We skipped a big jump from here to here that we didn't do from here to here. This is a smaller jump, because this is a 30-degree jump, and this is a 15-degree jump. So now this one, you can't see that well. I had to write so small, but the point is I'm going by 12ths. Here's a 12th, 2 12ths, 3 12ths, 4 12ths, 5 12ths, 6 12ths, all the way down to 24 12ths. But of course, 2 12ths reduces to pi 6. 6 12ths will reduce to pi halves. 24 12ths will reduce to 2 pi. So we do have all our convenient angles on here. But it's a way of reminding us that, hey, be careful when you label your x-axis. Don't just go willy-nilly. Don't have a 30-degree jump and then a 15-degree jump. That'd be silly. Okay, so what is sine's value? So these are the inputs, which are the angles. What are sine's outputs or sine's values? So remember, in this unit circle diagram, sine maps the angle to the y-coordinate. So when it's pi 6, it's a half. When it's 0, it's 0. So 0, 0, and pi 6 is a half. Okay? At pi 4, it's 1 over the square root of 2, which y'all rationalize. Very good. You've learned how to rationalize. You get square root of 2 over 2. That helps you. The only reason to rationalize is because it helps you to go, oh, this is about 1.4. Square root of 2 is about 1.4. So I get the 2, cut it in half, I get 0.7. Okay? Pi thirds, it's the square root of 3 over 2. What is that? Well, that's about 1.7. You cut 1.7 in half. You're about 0.85. It's actually a little bigger than that, 0.87-ish. You could maybe just round off to 0.9 and your graph wouldn't look too wonky. 5 pi 12 is not convenient, so we'll skip it for now. And at pi halves, sine is the y-coordinate, so sine is 1. And so forth. You keep filling this in. So I'm going to just quickly fill this in. At 2 pi thirds, sine is root 3 over 2. So remember, that's about 0.87. At 3 pi 4, sine is 1 over root 2, or about 0.7. At 5 pi 6, it's 1 half. At pi, it's back to 0. Then sine starts becoming negative. So it's been positive, all these positive y values, until it got to 0. Now we're going to start getting the negative y values. So we're going to have a negative 1 half here. We're going to have a negative 1 over root 2 here, and negative root 3 over 2 here, a negative 1 here. Here we're going to have a negative root 3 over 2 again, and then here we're going to have a negative 1 over root 2 again, and then here we're going to have a negative 1 half again, and finally we're back to 0. And then at 25 pi 12, so we don't know, but 26 pi 12, oh, that's going to reduce to 13 pi 6, which is coterminal with pi 6, and we'll get 1 half again, and the graph is going to repeat itself. This is called a periodic function, when it repeats itself over an interval of time called or interval of inputs, which is called a period. So a periodic function, it starts repeating itself. And of course, it repeats itself. If we were to go negative, we'd get the same pattern again in reverse, okay? So at negative pi 6, we'd have this negative 1 half, and then at negative pi 4, we'd have this, and so forth, and we just get it going the other way. So let's look at the graph now. Now, what I would do is I'd create this table of values first. When you're making your sine wave, when you're a beginner, eventually you'll just sketch it down because you'll know it so well. But when you're a beginner, to make sense out of it, make your table of values while looking at your unit circle diagram, remembering what it means, and make this table of values, and then carefully plot your points. So we're going to carefully plot our points. So when the inputs, now notice this is something that really throws students off. This is the x-axis, because the x-axis represents the inputs. So now all of a sudden x has changed its meaning. In this diagram, the inputs are theta values. Like we have an angle here, and it's a theta value, and the output is the y-coordinate. But on this diagram, x is representing the theta, and y is still representing a y-coordinate on the unit diagram, but it's also just the output. So we just think of it inputs, outputs, inputs, outputs, okay? So when the input is 0, sine is 0. Now, I'm going by 12. So this is pi 12, so that's not a convenient value. I'm going to skip it. So here we go, pi 6, which is 2 12ths. Well, that's a half. Sine is a half. It's all the way up here. Then we have pi 3 12ths, which is pi 4ths. So notice I'm going 1 12th, 2 12ths, 3 12ths, 4 12ths. 4 12ths will be pi thirds. That was supposed to be a 4. Pi thirds. So 1, 2, 3, 4. This is 5 12ths. Don't know what that is. 6 12ths is pi halves. 7, 8 12ths is going to be 2 pi thirds. 9 12ths is going to be 3 pi fourths. 10 12ths is going to be 5 pi over 6. 11 pi 12ths doesn't reduce, and then we have pi. Okay, but what is sine at pi 6? It's a half. What is sine at pi fourths? Well, it's 1 over square root of 2. But what did we say that was approximately? Oh, it's about 0.7. So at pi fourths, we get about 0.7. And then at pi thirds, we get root 3 over 2, which is almost 0.9. And then at pi halves, we actually hit 1. You know, I might ought to have a ruler out here because you'll have a tendency, look at that, I had a tendency to drift a little bit to the left. You'll have a tendency to drift over to the right or to the left. And if you do that, you're going to get a really wonky graph, okay? So you need to maybe use a ruler. If you're like me and kind of have a tendency to just move your hand willy-nilly. All right, we're going straight up from here. 2 pi thirds, sine is going to be 0.87 again through root 3 over 2. So that's almost to the 0.9 line. 3 pi fourths, well, it's going to be 1 over root 2, which is about 0.7. 5 pi 6, we're back to being a half. So there we go. And at pi, we're back to 0. Okay? Now what? Well, this is 11 pi 12ths. This is, what am I saying? This is 12. So this is 13 pi 12ths. This is 14 pi 12ths. So this is 7 pi over 6. And we know that sine at 7 pi over 6 is going to be a negative 1/2. So I come down right here and make sure it comes straight down. And there's a negative 1/2 right there. Okay? So then we have after 14 pi 12ths, we have 15 pi 12ths, which is the same thing as 5 pi over 4. And then the next one's going to be 4 pi over thirds. And then we're going to skip one to get to 3 pi halves. How did I know to skip? Well, you count by 12ths, and if it doesn't reduce, you know, this is 13, 14, 15, 16, 17 12ths doesn't reduce. The other way I know it skips is where do the breaks happen? Well, between pi and 7 pi 6 and between 4 pi thirds and 3 pi halves is where I have the bigger, see this is a small arc and this is a bigger arc, twice as big as that arc, okay? So I knew that between 4 pi thirds and 3 pi halves there was a big arc, so a big jump. So there's gonna be a big jump here and I'm gonna have one here. It's gonna be 5 pi over 3, 7 pi over 4, and 11 pi over 6. Now at 5 pi over 4, we are back to sine being a 1 over square root of 2, but it's negative this time, and so that's about 0.7. At 4 pi over 3, it's back to root 3 over 2, but negative this time, so almost negative 0.9. And then at 3 pi halves, it should be all the way down to negative 1. Then at 5 pi thirds, we're back to it being root 3 over 2, so it's going to be, line up with that one. At 7 pi fourths, it's going to line up with this one. And at I can't even read my own handwriting, so Taylor Milliken is right. This is pretty bad, but this was supposed to be 11 pi over 6. This is what this was supposed to be, so I don't know what that is, but that's 11 pi over 6. You know, what's next on the unit circle, you know? After 7 pi 4 is 11 pi 6, then there'll be a 12th in there, and then there'll be 2 pi. Okay, so 11 pi over 6, then a 12th, and then 2 pi. And 11 pi over 6, this tells me this is going to be a negative half, and then we get to negative 2. Now, some of you are going to be tempted to draw a V, but it's not a V. It's a nice curvaceous Beyonce curve. So here we go. It's not Taylor Swift, it's Beyonce. Both of them are phenomenal talents and beautiful women. But this curve is a Beyonce curve for sure. There is one period of the sine wave. So this is y equals sine of x. And I have graphed it for one period. Or actually, you could say one cycle, which will occupy a period, at least period, I should say, but we don't want to get bogged down in details. Now, some of you are going to be tempted to put arrows. Well, you don't put an arrow. An arrow means it keeps going down, down, down. It's not going to do that. What's going to happen over here on the negative side? Let's put in a negative pi 12ths and then a negative 2 pi 12ths. So this is a negative pi over 6. Well, negative pi over 6, the angle rotates this way, so it's coterminal with 11 pi over 6, so sine is a negative half. So at a negative pi 6, the sine wave is here. So you see the graph is coming down, but you don't draw an arrow because it's never going to get past negative 1. So what you do is you do this dot, 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 and that tells the reader when you see dot, dot, dot in mathematics, it means and continue. So I'm going to put a dot, 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 and that means the pattern continues. So this pattern continues. So from 2 pi to 4 pi, it's going to do this cycle again. That's what makes it a periodic function, is periodically it repeats a cycle of itself. And this is a sinusoidal wave. Now, it has some characteristics we need to talk about, some attributes other than the period. So the period is 2 pi, okay? That is the interval of inputs over which it will complete a cycle. Then it has something called the amplitude, which if you find the center point in between it. Now, if I shifted this up and down, it wouldn't be 0. But in this case, it's right when y is 0. We're right in the middle of the wave, okay? And so the height from that median line or center line to the highest point is called amplitude. So the distance from this 0 line up to the highest point, which is 1, is called the amplitude. So the amplitude is 1. Math made simple. Simpson math.